Welcome everyone to Quality Improvement Methods. Today we will talk about the Minitab. We will have a review for all the quality Minitab, all the quality tools for the Minitab. Before we proceed with the Minitab tour today, if you have not downloaded the Minitab or you don't know how to download it, I will share with you the screen for the web page that where you can download the Minitab, and then we will start our review today. So let's share the screen. Okay, this where you can find the Minitab on the hub.com/Minitab. You scroll down until you find the Minitab statistical software. There is an offer for students to register or to rent the software application for 3 months or for 6 months or 1 year. The 6 months cost around $32.99. If you press on rent now, it will take you to the prices. Those the two options. Here is the 1 year option, and here is the 6 month. You will need your university email or your institutional email, your educational and institutional email, in order to download and be eligible for this offer. This is compatible with the Windows desktop. Also, there is a version for the Mac, and from here you will get to download the software, and then you will receive the activation code on your email to activate the software package. Also, there is a 30 days trial free if you would like to. So this is where you can get the Minitab. Again, here is the website, and this is the link. And now let's proceed with our tour for today. Today we'll have a review for all the quality tools that listed here in the Minitab. Here under Stat, you see a Quality Tools tab, and it has several tools. Some of those tools we have covered them in previous sessions, like in define phase or in the make framework. Some of those tools are new. For those new tools, we will introduce them today. We will see how we use them, when we use them, in case of a real application, how you can use the Minitab, or to solve also a problem or a questions you have in the exam. So we will proceed with the tools with the same order here we have. We will start with the run chart until we go to the summary plot. Step by step, we will show you how we do it on the Minitab, as well as also we will take an example for each tool. So let's proceed with our first one, which is the run chart. For the run chart, it was explained earlier in other session in the measure phase of the make, and we have talked there. You can watch the lecture where we use it and when we use it. So we will not give more details about that since it was already explained. But anyway, in general, the run chart helps you to find the patterns in the, or if there is a non-random patterns or trends in the data, that it helps you to detect it. And also we explained before that it is different than the control charts. The control charts work for detecting or monitoring the stability of the process, and you need a statistical formula to do the control charts because it needs to calculate the control limits, which is upper, lower control, and center line. Here in the run chart, you just enter the data and leave the run chart to demonstrate it over the time. As the example here we have today, a quality engineer wants to evaluate how consistently a radon detection device measure the amount of radon. The radon is like إشعاع أو radiation. The engineer measures the radon level twice a day. So he measured it 2 times every day for 20 days. Construct a run chart to look for evidence of non-random patterns in the radon measurements from membrane devices. So this radon level, it was measured using this device, and this is how they use it. They use it twice per day for 20 days. And the data is given here. I will expand the sheet so you can pause this video and you can copy those readings in your own to try it at home. So this is the data here, the given data. You can pause and you can copy those numbers. Now we will move on to the remaining numbers in the data. Okay. So how we construct the run chart, as we see here in the figure, you go to Stat, and as we said, we will start with the first one here, run chart. And it says if you just leave the mouse there, it shows you the purpose of this tool. The Minitab itself, it shows you that look for patterns in your process data and test for non-random behavior. So it shows you the patterns that we already explained them in the quality control course, and also the non-random behavior for the data. So in this case, what you will do is you are going to press on the run chart, and then it will open this window for you. As soon you press on this cell here, you will have it empty like that. So you just double click on the radon level here. That's the data from column C2. So it will pull the data here. The same for the day. You will have it like that, empty. And this is the subgroup size because we have 2 readings every day. And then you double click on the day, and you leave everything else as is, and then you just press OK to get the chart. And here is the chart. This is the mean for the data, and those also the readings. But since we have more than one reading every day, the blue dots, you see them, this is the reading for one of those sample size, and the others are given in the gray dot. You can tell from the points here in the up and points here down, there are clustering, or let's say there are points that seems to be out of control and need more investigation. You can use the control chart in this case to dig inside this data and analyze it more. You can see that it was here stable down, and then it was increasing until this level, which is really high. It seems to be there is something happened here. Other than that, it looks like then it becomes stable again. So there is a trend here, and also there are some points low. So it can also be verified from those values. Those value, if you have confused in terms of the visual picture about the trends, you look to those p-values here. The p-value should be greater than 0.05, since we are using the 95% confidence level. And here we have most of them, or for the p-values, for the trends, for the oscillation, the mixtures, the clustering is the only one that is less than 0.05, and that's an indication for special causes that also may be refer to the sampling or the measurements or the device they use. So this is one of the things that tells you if you have a 0.05, less than 0.05, then there is something need to be investigated more, or the process need to be monitored in details more. If all the values came more than 0.05, that seems to be a normal run chart in that case. So this is a very simple tool, and also shows you the mean, as we said, and that also help in terms of analyzing the data around the mean, up or below the mean. Moving on to the second tool we have today, we have the Pareto chart. The Pareto chart is one of the other tools also we have explained earlier in the measure or the analyze phase in the domain. You can refer to those videos there, and you can watch in details more about the tool. So the run chart, mainly we use it to prioritize the defects. And let's say you have a limited budget to solve a problems in the organization or in the process. You have implemented Six Sigma project. You start to measure the performance or the quality level, and you start to collect the data to analyze the root causes of the problem. You found that the defects come from several factors. In that case, if you have a limited budget to solve or resolve or improve the process, the Pareto helps you to prioritize which one should I focus first on, which one it will resolve most of the issues and improve the process quicker. So that's where we use the Pareto chart. The Pareto chart example here we have is an inspector for a customer compliance investigates source of compliance to prioritize improvement projects. The inspector tracks the number and type of defects in the process, construct Pareto chart to prioritize the defects that the inspector found. So inspector or engineer or auditor, name him, the function he did is to find those defects cause the customer complaints. عندنا شكاوى من العملاء, whether internal or external customers or customers, both works. And the information of the frequency of those complaints comes from the documents 40 times, from the product quality 32, the packaging 11, the delivery 7, and then other complaints or complaints comes from other categories. It could be more, depending on the case. So basically, you enter those information as you see it here in the worksheet in the Minitab, and you go to Stat, and then you go to Quality Tools, and you press on the Pareto chart. The same here, you will feed the cells from the column here. So you press on the customer compliance and the frequency, and then you press for the Pareto chart. Okay, and here we go. We have the chart. Now, how we can analyze it? How we can use it for prioritizing? Since we have a small data here, even though you can just tell easily by looking to those first two, but sometimes you have a very close numbers, and you have many categories for the defects. So it would be better to use the Pareto in that case. But looking also to the Pareto give you this feature that you see the percentage related for each category. So for example, the documents here is 42, and the product quality is 34% from the overall frequency of the defects. And you see the cumulative sum. So That tells you also the adds up from the previous category until the one where you are looking at. And if you look to this curve here, that helps you to identify if you are going to apply the 80-20 rules. So you can see where is the 80% comes, and you see it is intersecting here. That's mean if you are going to solve the documents and the product quality defects, you would resolve 80% of the effect of that problem. Go to the session and explain that in the previous sessions in the make about the 80-20 rule. If you have, as I said, limited budget, then you will start definitely with the documents will resolve 40% of your issue. But if you have if you want to use the 80-20, or the question asks you to apply 80-20 rule, so you will have to select the one that shift to the 80. So in this case, even though if you come to the 80 and intersect partially with one of the categories, mainly 20% of those, that's mean the first two, it will cover 80% of the effect of that problem. If you have enough budget to resolve them, then and you don't have the need to prioritize those defects, then you can just resolve them all. But this is how the Pareto works and when we use it. And in the case of the 80-20 rule, so 20% of the causes resolve 80% of the effect. So 20% of the causes, that's mean here the product quality in the documents will resolve 80% of the effect of the problem. A note here that if you press on the tab here, you can copy the graph. Also, you can edit on the graph. For example, here you can edit the title, you can change the font. So you can have a modification, you can add shapes, text, and so on. So this is just to let you know how also the feature in terms of copying the figures and add them in your answer sheet if you are going to work this on for a case of the project or an exam. Okay, so let's move on to our third tool today, which is the cause and effect diagram. Also, this is one of the tools that we have investigated and discussed it before. We use it to find out the root causes of the problem. We try to categorize those root causes. We can also sort them up using the cause and effect. So it will help us in analyzing the problem. Sometimes it comes before the Pareto, and in the Pareto, after the investigation and finding the major all these causes, you can put them in the Pareto to prioritize them and see which one you should focus first. So in this example we have today, a safety auditor discovered that cars accidents happen most often because of lost control of the car. The auditor meet with car insurance companies, شركات التأمين, drivers and the police traffic to brainstorm potential causes, find ايش الاسباب الحوادث و losing الكنترول في الحوادث للسيارة, create cause and effect diagram for the founded information by the safety auditor to organize the causes that he identified. So he gave you these identified causes for losing the control or lost control of the car. So the main effect we have, usually you have one effect and then multiple of causes related to that effect. And this is how the cause and effect, or the fishbone, as we said before, we call this tool also fishbone diagram or Ishikawa diagram. How we can construct these information? You copy this information to the Minitab here worksheet, and then you go to stat and then tools and then cause and effect, and you start entering the information here. How we did that? The default comes in this way. So the data either in column or constant, that's mean you are going to enter it here. But here in our case, we have it in column because each of those category he found, they have a slippery road category. That's mean the oil in the road or ice or rain or snow. That's why they are losing the control for the car, the drivers, or mechanical failure as another category. stuck accelerator اللي هو دواسة البنزين تكون معلقة من الداخل. بريك فيلير يعني مشكلة في الفرامل. driver error يعني now issue from the driver himself. poor training يعني ما كان يجيد عملية قيادة السيارة. reckless, poor reflexing, all these related to the driver himself. And here we can see this category that says the brake failure. It could be coming from not changing brake pads or not changing brake oil. So basically, lack of maintenance for the brakes. It could be the brake failure. It could be more than this, but this is based on the information we have. But if you notice, this is what I would like to highlight. If you notice the brake failure, it was a subcategory, or it was one of the sub-causes under the mechanical failure. So basically, the brake failure, it's under the sub-causes under the brake failure, which is under the mechanical failure. So you have to pay attention to those data you have and make sure that none of those are, like this example here, are placed under one of those. For example, poor training, or let's say oil, for example. It could be another category here for the oil, and there is maybe an accident happen, there is no regular checking for the road, whatever was the other causes that cause that oil in the slippery road. Also the stuck accelerator, this is can be another category, and you can find what is the causes. If you recall the 5 whys tool that we have done it in the analyze, you can use it to find what could be the causes for having an accelerator stuck. So this is only here was an example only for the brake failure as a one category under the subcategory in the mechanical failure. So how we deal with this data here, how we enter the information. So we start with the first one here, the slippery road, as long as the slippery road is not sub of any of those information here. So we don't see slippery road here on the cells inside the category. So it is a category by itself. Now we have learned about how we use the names for the categories that we have done it in the cause and effect. If you recall, we have used a material, machines, manpower, mother nature, measurements. All these we used to have the methods also. So we call that the 6M. Or you can use the name of the category, you have it here. So instead of, so let's start with the first one, the slippery road. Let's say the slippery road here. The slippery road, it was empty. You can start at any cell here as long what label you are going to give that cell. So let's say we are going to start with the slippery road. So you will press on the slippery road here, double click, so you will see it appear here, okay? Now for the slippery road, what will be the category you would like to to use, you can, this is the default category, it's written here, environment. You can label it also with slippery road if you want. So the label in the cause and effect diagram will be slippery road for that category. You can use environment, or you can use mother nature, as we did in the example we had, or in the slides for the cause and effect. We have talked about the 6 M's, and one of those M's is mother nature. So let's move on to the mechanical failure. The mechanical failure, I place it here, and you can place it anywhere in the column, depend how you label the information. So you will have it empty like that. What you will do, you will double click. Now, it says here machines. You can replace the machines, or you can leave it as it's given here. So this is editable, those cells. You can use mechanical failure, or you can just rely on the 6M abbreviations. In the mechanical failure, we have the brake failure has another subcategory, which is this one, the column C5T. So what you will do, you will press on the sub here on the right, and when you press, it will open another window for you. And that window will be for the subcategory under the mechanical failure. You will have this one here. You will have this guy here empty. So what you will do, you can use any branch, by the way, here, depend on where you would like to have the sub causes, and then you press double click on the brake failure. So the brake failure will be, the data will be taken from the column of the C5T. So the no changing brake pads and no changing brake oil, it will be placed under brake failure. You can have the stuck accelerator, if there is a data for the stuck accelerator as a sub branch. So you can have the stuck accelerator written here, and also you have the data, let's say C6, it will be stuck accelerator, and you will have more information or more causes related to that. When you press OK here, it will take you back to the main table. So you return to this table and continue. So now we are done with the slippery road, the mechanical failure, and the brake failure. Since the brake failure, it's sub-branch under the mechanical failure. Now let's move on to the last one, which is the driver error. The driver error categorized as the manpower, since it is related to the manpower category, or you can, as we said, you can replace the label here and you can just have it driver error. Now the effect, you write the effect here. Our effect in this case, it was lost control of the car. This is the effect. ايش هو الافكت؟ هو very similar to السيمتوم. يعني ايش اللي ظاهر عندنا في المشكله، او مسببات اللي هي الكوزز، والنتيجه للكوزز او المسببات هذه يكون عندنا هو الافكت اللي هو النتيجه او العارض او السيمتومز from those causes. Okay, so we write it here اللي هو lost control of the car، يعني فقدان السيطرة والتحكم بالسيارة. The title of the figure, you can type it here if you want, as you can see here, cause and effect diagram for lost control of the car. For this option, you can either don't label the branches, you can have them without labels. You can also hide the empty branches. For example, we don't have branches related to methods or to measurements, okay? In some cases you may have, in some others you may have other categories are not having any related to that effect. يعني ممكن يكون عندنا another example، the manpower was not one of the causes. It could be methods and measurements instead of the manpower. So instead of having the fishbone diagram with those empty lines, you can check on this one here. Don't display the empty branches, so it will hide the methods and measurements. I will show you how it looks, and also I will show you if we didn't tick on this one, how also it will look. When you press OK, the figure, it will come up like this one. Lost control of the car will be the effect, and then the cause is manpower. Here are the label for the branches, material, environment. You can hide them if you want. You can change the name for those from here by typing the name you would like to. And the sub branch for the brake failure, you can see it comes from the brake failure, no changing oil and no changing the brake pads. So if I press OK and I let the empty branch appear, you will see the figure looks like that. The methods, measurements appeared, but they are empty because we don't have causes. So that will look more neat compared to this one. Double click on the figure, so it will open, and then also you can enlarge the screen to zoom in if you would like to read those. And they are readable, so if you copy the figure from here, it will be, or save the graph if you would like to. It will be clear when you zoom in. It will keep the resolution good in the picture. So this is how you do the cause and effect. This is the one without the branches that are empty. I prefer this one because it's more clean. There is no branches that just disturb you. Okay, so this was for the cause and effect diagram. Now let's move on to our coming tool, which is individual distribution identification example. This was not discussed in this course. It was discussed on the quality control course though, but today also we'll give where we use this tool and how we use it, how we get the use of that tool. So let's just prepare. Yes, this is the example. Well, the distribution identification, it's a tool. We use it to identify and determine which distribution fits the data you have. So you have a data and you would like to know which distribution they are following, okay? So that's where we use the individual distribution identification. It's a very useful tool. You have received the data. You were not the person who was collecting the data. You don't know this data, whether it's a normal distribution, Weibull, or exponential. Name it. There are plenty of different distributions for the data. So use this tool to show you which best fit can fit your data, so you can know the type of data you are dealing with. The example here we have a quality engineer for a nutritional supplement company wants to assess the calcium content in the vitamin capsules. عندهم حبوب كبسولات فيتامينات فيها calcium, and he would like to, or he collects already a random sample of capsules and records their calcium content. فجمع عينات من هذه الكبسولات وبدأ يحلل نسبة الكالسيوم فيها. To determine which statistical analysis is appropriate for the data. So he would like to apply some analyze tools or statistical analysis tools, but he would like to know which type of data. The engineer first needs to determine the data distribution. Use individual distribution. It could be a question. Use individual distribution identification to determine which distribution best fits the data. So you have a data, for example, like the one here, Also, I will leave you to pause this video and copy these numbers in your own. These are the calcium readings from the capsule samples that a quality engineer he collected, and he would like to know what type of distribution fits this data. So we use this tool now to identify. It could be fitting more than one distribution. Well, we know that the normal distribution is preferred because you have plenty of tools. You can use them to analyze the data when it's normal. Um, um, there are ways we will learn today how we can identify the best distribution, as well as how we can transform data to normal if it's there are some indications or signals from this raw data tells us that this data can be transformed into a normal distribution. So how we conduct this analysis, you go to stat to quality tools, then you go to individual distribution identification. It says here in the box, identify an appropriate distribution or transformation. You can read that in the box here before you perform capability analysis, because assuming that now the capability analysis, it needs the data to be normal, but we will see how we can deal in that case if we don't have to, or if we don't have normal data. So what we do, you will have this window open. Basically, you have the data from the single column here. You just press it. If there is subgroup, then you enter the subgrouping for this data. And then you leave everything as the regular setup. It will check all the distributions, the most common distributions, and you press OK. And then when you press OK, this screen will pop up to you with all these figures and tables and readings. Let's analyze them. Let's see how we can see the best fit. Basically, the easiest way to do that is by finding the p-value, and the p-value for each distribution has to be greater than 0.05. So either by looking to the figure or in the information here, that's the column for the p-value. Also, you can look for each one, but that maybe will take more time from you. Now, for the normal distribution, p-value is 0.046, so it's not 0.05 or is not greater than 0.05. That means the data, even though it looks like close to be normal, even from the figure, we can tell that, but it is not normal distributed. Also, the p-value for the log normal is 0.06, I think is not clear. Let's go to the here. Yes, here it's more better. We have 0.085 and the 0.046 for the normal, and the Weibull 0.01. We have a large number in here, the 3-parameter Weibull distribution. Also, we have the log normal also is acceptable. The box transformation is 0.3, and we have here some values for the LRT, which is the likelihood ratio test, and these we use it if we would like to identify if the additional factor or parameter added to this data will make a significant improvement or no. This is how we use the LRT, the likelihood ratio test. If the p-value is less than 0.05, then it suggests that if we add another parameter, that will have a good improvement to the data fit. So if it is less than 0.05, as we see here, it is less than, in all these cases are less than the 0.05. But now you have more than one distribution. As you can see, it could be a fit for the data. As we can see here is 0.5, 0.08, 0.3, but note and look to this one here, 0.986 for Johnson transformation. And what does that mean? It means that the data can be transformed into normal distribution with a good fit, can come up into 0.98 if we apply the Johnson transformation. Johnson transformation used if the data, they are not normally distributed, but can also, like this case, can be transformed into normal distribution. If we have the Johnson transformation value, p-values greater than 0.05, that's a good indication this data can be transformed into normal. If this was less than 0.05 and the normal was less than 0.05, you will choose the distribution that has higher p-value, like in our case here, 0.5 for the 3-parameter Weibull. There are also other statistical methods like center limit theory, and this is explained in different courses in statistical and probability. But in the most cases where is the quality applied, and in most data we are dealing with for the process, the machines, the most of the time they are dealing with normal distribution and normal events. It is one of the largest distribution that carried most of the events and cases and measures that we are dealing with. But this is was an example for a close to normal distribution. We have other good distributions, but here the Johnson transformation tells that it can be having a good fit for normal distribution if we apply the Johnson transformation. We will explain the Johnson transformation after this one, but to answer the question here, you will refer to the values. Now, going back to question, how we solve it after we get this data here. You go and find all the p-value greater than 0.05 and you identify those distributions has more than 0.05, and then you will list them and says those data are having a good fit for the data. And to order this data, you will start with the highest to the lowest. And in this case, the highest one is the Johnson transformation. And then you will list all the remaining. And if the question also asks you if the data is not normal, is there a chance to be transformed into normal using Johnson transformation, then you check the value of the p-value of the Johnson transformation. If it's greater than 0.05, then you say yes. If no, then you say no. And in the next step, we will see how we can transform it. But this is how you use the individual distribution identification tool to determine which distribution best fits the data. So you order them from highest to lowest p-value that is greater than 0.05, and you highlight the highest one and you identify it. This is how you deal with the the individual distribution identification. As I told you, the LRT value here, if it's less than 0.05, that's mean the adding additional parameter to the distribution, it will significantly improve the fit. So it will improve the fit if you add parameters for the 3-parameter log normal, 2-parameter exponential. If it was identified less than 0.05, that's mean adding parameter will improve it. But adding parameter, could be not optional in your case for the data or for the process you are dealing with. But this is just to show you and explain to you what does the LRT mean. But we are not going to use that in our identification. For the best fit, we will rely only on the p-value. Now we learned about the distribution identification. We will use the same data here, the same data. So when we are going to the next tool, which is the Johnson transformation, you will use the same data. You can go back and pause and copy those values from here. And let's move on to the Johnson transformation and see if we use that tool, how we can transform that data into normal. The use of the Johnson transformation is to transform the data to follow normal distribution. And the example is, for the same example, the quality engineer for the nutritional supplement company assessed the calcium, as he did before, from his past experience, or from, let's say, the previous example we had. The engineer knows that the data are skewed or right skewed, and the engineer wants to perform Johnson transformation to transform the data to follow normal distribution. He had the p-value from the previous tool we have used that tells him that this can be transformed into a normal distribution using the Johnson transformation. How we do that is very easy and simple. You just go to the tool Johnson transformation here, okay, and you press on that one. You enter the calcium or the single column here by double clicking on the data, and for where you would like to store the transformed data, so the results after the transformation for that data, where it will be placed. So you type the cell name. I put that name, transformed data, for the column C2. So you type this one here, and this will be empty. This is the result. This is after the transformation. The Minitab will store the results here in this column. So when you press OK, this will be filled. This is not given from the example. So these are results of the Johnson transformation, okay? This is only the given information. This is the result. And as you can see, some minus and plus values, and even the description for the Johnson transformation says that can be used for a variety of non-normal data, including negative numbers. So the negative numbers given here, it's a transformed using mathematical formulation, not arbitrarily, to give you the exact statistical analysis for the tool, but with a normal distribution fit. The p-value here we have, before we do the Johnson transformation, as we did in the previous tool, it was 0.046. After we do the transformation, it becomes 0.986, and that's very good fit. As you can see how even those dots here are away from the center line of the probability plot, even here. Now you can see more dots and more data are fitting this normality or the probability plot. So this is how you transform the data, and then you can deal with this data and you apply the process capability analysis or any other tools that require to have control charts or normal distributions. So that was for the this tool. Let's move on, which is our following tool, the capability analysis. And the reason maybe for the transformation was to show you before conducting the capability analysis, it would be better to conduct the identification for the data and make sure that it can be normalized before you use it. Maybe the question in mind, okay, if I didn't use it, it will work, the tools, it's okay, it will give you an identification, but for best analysis and consistent results and reliable result. Data, when it's normally distributed, it will be better for analysis and for long-term improvement and monitoring. That's why, and most of the time in the cases need just to review how is your measurements, how you're doing the sampling, in order to have a data either normal or it can easily normalized. And as we said, any data can be changed into normal using the center limit theory. Okay, so let's move on to the next tool, which is the capability analysis. The capability analysis, it's discussed also in the quality control course. We will recap briefly what is the capability analysis. It's used for evaluating the capability of the process to perform within the specification limit. My specification limit, let's say, I deliver pizza, okay, to from the restaurant to home. The delivery process, it should be within 15 to 30 minutes. Depend on how many cars you have, how many neighborhood you are serving, how many order or request you are receiving. Then you can collect your data, your current data, and put them here in the capability analysis to check whether your process is capable to perform and deliver the pizza within this specification limit or no. So the specification limits tells you before you do control charts and you check the stability of the process, do the capability analysis to make sure is the process capable to perform and meet the specification before I check the stability in the control charts. So that's where we use the capability analysis. We have an example here, an engine manufacturer use forging اللي هو forged يسموها نوع من انواع يعني الصلب في التصنيع process to make a piston rings so it can يعني carried high pressure and temperature. The quality engineers want to assess the process capability. They collect 25 subgroups of 5 pistons rings and measure the diameters. The specification limits for piston ring diameter are 74 millimeter plus or minus 0.05 millimeter. Use process capability analysis to study if the process is capable or not. So we would like to make sure if this process is capable or not using the capability analysis. Remember those values for the CP and the CPK when we say it's okay, when we say it's not acceptable, and when it's good. The CP has to be greater than 1.3 to be, sorry, it has to be between 1.33 and 1.67. For the CPK, it has to be between 1 and 1.3. If it's greater than 1.3, that's mean it's good capability, and 1.67 for the CP. The CP is for both of them used for the capability, but we rely on the CPK to check the capability. It gives us the better picture about the capability, but both of them are useful. As we explained earlier, you can refer to those in the quality control, one for the centering the data and one for the variability. So let's move on to the process capability. Here is the data. Again, I will expand the sheet so you can pause this video and you can copy those numbers. Okay. So these are the diameter measured for the piston rings. The specification is given. It has to be 74 plus or minus 0.05. And the sample they are using 25 subgroups of 5 piston rings. Okay. To conduct the capability analysis, you go to capability analysis, normal, and you select the subgroup size, 5, because it says the subgroup is 5, and the data for the diameter, you will double click on the diameter column. The lower specification and the upper specification, you will enter it manually by subtracting the target value minus the specification, and that will be the lower, and you add it to the target value to the margin or to the tolerance, and that will be the upper. So you have to pay attention to that point, and then you will press OK, and the distribution or the process capability analysis will come like that. Here is the figure to show the normality of the data, and the main values are here. CP is 1.66 and the CPK is 1.62. Both of them are greater than 1.33, and that means they are acceptable, and this process is capable in meeting the requirements that are specified to do it. Moving to a tool similar to the capability analysis, actually it is the same but with additional information called capability six-pack. So if you work out hard, you will move from just process capability to have a six-pack. Okay. Now the normal capability six-pack give you information about also evaluating the normality of the data and the stability and the capability of the process. This is a feature in the Minitab. You can do each one of those functions individually. For normality, you have normality check, you have for the normality plot, and you have the identification for the distribution. For the stability, you can do control charts based on the nature of the data you have, and the capability analysis, the one we just did, this is a capability analysis. But that chart, it collects them all and put them in one figure. The same example, we have done it here. We will use the capability six-pack and do it. So the same data, no need to change it. You can use the same data, and you apply the capability six-pack here. Okay. The same, all the information, and when you press OK, it will show you all these figures, which is nice to summarize the information about. Regarding the XBAR chart here, now if this data eligible to XBAR are, as you can refer to the quality control charts, it depends on the sample size and the type of the data you are dealing with. That's one of the things you have to pay attention before you use the process capability six-pack. Other than that, it shows you the p-value here. That is normal. The data is the p-value is greater than 0.05, so that means the normality plot tells that the data is normally distributed. CP and the CPK value, it's given here. The specifications, you can see them here in the last line, where is the red dashes, and you can see the overall how this data are fitting the specification. It's below the specification limits. That means it's performing well under the specification limits. And here the data or the samples and the value for all the samples you have collected. So it's an additional feature if you would like to, but as we said, this can be dealt individually, and this one also, each one of those can be done individually based on the information, and especially for the control charts, depends on the how you collect the sample size, the type of the data. Then you can judge the control charts you are using. As you can see, the capability analysis there is for the non-normal capability and binomial, Poisson, all these distribution. But these are beyond this level of the course. We are dealing with the most cases that, or the most frequent cases we are dealing with, it's the normal distribution, and most of the statistical analysis are dealing with it. But there are always a way how you deal with non-normality, as we briefly explained previously. Now, moving on to our next tool, which is the tolerance intervals. In the previous example here, the tolerance was given. It tells you that's the specification, and these are the 0.05 plus or minus the tolerance. Here, the tolerance intervals used to calculate. You have the tolerance intervals tools to calculate the tolerance levels in the data you have. So here is the opposite. We find the tolerance level in our data, as we have here for the example we see here in the slide. A quality engineer wants to assess the lifespan of the light bulbs that a company manufactures. So عندنا لمبات, he would like to assess العمر الافتراضي, lifespan for this light bulbs. The engineer collects a random sample of 100 bulbs and records the burn times to failure. يعني جلس يشغلهم إلى يشوف بعد كم ساعة يعني بيخربوا. The engineer wants to calculate the lower tolerance bound, which is the burn time that at least 95% of all the light bulb exceeded. يعني هو يبغى would like to find a lower time اللي 95% من المنتجات حقته يعني تعدي. Let's say he wants to have a minimum time, خلينا نقول بالسنة مثلا 3 سنوات. A lower specific, or the tolerance in that case will be, the lower bound is 3 years. So 95% of his products will exceed 3 years. And this is a very good useful tool, by the way. Use tolerance intervals for normal distribution to help the engineer in calculating the lower tolerance bound for the light bulb. He gives you the hours for the 100 bulb he collected. This is the record until they got burned. So he calculated that time for them, so he can identify or use them for the tolerance intervals calculation. Again, I will ask you to pause maybe this video and copy those numbers, and then I will scroll down, then pause it, and if you would like to. Okay, so how we conduct the tolerance intervals for this example, we will go to Stat, Quality Tools, and then we go to tolerance interval for normal distribution. The question, by the way, stated that it's normal distributed. Unless the question asks you to check normality first and provide evidence for normality, then you conduct this tool Or if it is non-normal, then you will use the non-normal tolerance interval. So now in this example, we have for normal distribution, you have either summarized data or one or more sample in each column. In our case, we have all the samples here given in the column. So you just put them and you put 95 confidence interval. This is the minimum percentage for the data. And in our case, he said he wants to find the lower tolerance bound. That means he doesn't want to have the maximum. And obviously, in this case, you want the maximum infinity. So whatever is more than the minimum, it's acceptable. So he wants to find a lower bound. يعني ما يبغى يشوف الماكسيمم، يبغى اللمبة تعيش للعمر كله يعني. لكن المينيمم he doesn't want it to be less than, let's say, يعني a specific number. So he wants to find this lower bound. So in this case, if we want only the lower bound, we have to go to option, and the confidence level has to be 95, since he said that 95%. And then you choose whether two side, that's mean upper and lower, or lower bound or upper bound only. In our case, will be lower bound only. So we'll choose the lower bound and then we press OK, and this will pop up to you. That's the figure for the tolerance interval, and basically you can find the data here. And by the way, these are hours. So the lower bound for those bulbs, it will be 1085. We can say 1086 hour. That means 95%. The engineer now, he's 95% confidence that at least 95% of all the light bulbs will exceed this approximate number, which is the 1086 hours of burn time. And this will be the lower bound for our tolerance. And also we have to always check the p-value to make sure that the normality test, how was it, since we are using the tolerance for normal distribution. So this is also a good trick that you have done both of them in the same tool. It's 0.34, and it has to be, as usual, greater than the alpha value, which is 0.05. And in this case, you have done both of them. So if the question asks you to do so, you can do it in the same tool. Now this is checked for you, the normality, and also gives you the lower bound, which is the 1086. And that's how the engineer can be 95% confidence that 95%. So pay attention to those. There is the 95% the confidence for the test, and 95% of the amount of the light bulb exceeding the 186. And those are, you have to identify them here. Pay attention to this one. Here is the minimum percentage of population in the interval. That's mean at least 95% they are greater than the lower bound. And here the confidence level for the test. Here they are matching 95, but you have to pay attention. There is different. This is the 95% confidence, يعني ثقتك في هذا الاختبار. And 95 here 95% من المنتج حيكون أكبر من اللمبات، حتكون الأكبر من الساعات التشغيل حقتها أكبر من 1086. الرقم اللي أوجدنا 1086. So this is for the population حق الإنتاجية حقتك, the percentage in that production. هذاك الاختبار الثقة اللي هو confidence level. So pay attention to those. They are different even though they are equal here. Now let's move on to our tool, which is the same, but here now for non-normal. If we are using non-normal data, then we want to do the tolerance and for a non-normal data. So it's the same concept. You want to find the tolerance intervals, but here for a given data, they are not normally distributed. Now, another quality engineer wants to assess the lifespan of the light bulbs that the company manufactures. Sorry, this is the normal. I'm sorry. Yes, here is the one. It's the same. That's why it's kind of confusing. So the tolerance interval for non-normal distribution to calculate the tolerance bound for given non-normal data. Okay, here is the identification. Pay attention. The identification between them, one used for normal data and one for the non-normal. Manufacturer wants to evaluate the variability of their paper bleaching process. عملية تبييض أو الورق. The manufacturer randomly collects 200 samples of bulb and record the brightness level. عندهم يعني measurements they are using is a brightness level, نسبة الوضوح أو السطوع في الورقة. The manufacturer wants to calculate a range within which the brightness of at least 99% of the batch are expected to fall. يعني they want now, pay attention to the wording here. It was saying in the previous example the minimum or the lower. Here it says to expect it to fall between, fall a range within those keywords. He wants to find upper and lower range within to fall. هذه معناها بين قيمتين. Okay, so he wants to find upper and lower. Okay. For the 200 non-normally distributed samples, even if it didn't say that, the test for the normality will identify that if you have used that one by mistake. But if it's specifically that to use the non-normal, then don't do that. You use the non-normal distributed sample test. Calculate the tolerance interval. Assume Weibull distribution for the data. If it says, then you choose the Weibull. If it didn't, then it could ask you to identify the best fit first. So you have to use the identification distribution fit first and find the highest one. As we said, you have to order them based on the highest. So you will select the highest one, and then from the highest one, you will choose it here as the distribution fit. So it can be in different scenarios. The data for the brightness of those collected samples are given here in column C1. Again, I will expand that so you can pause the video if you would like to copy the numbers and try them your home. We have 200 samples, so it's a quite big data. Okay, so these are the data for the collected measures for those pulp. Okay, now how we do the tolerance interval for the non-normal? Easy, as we did for the normal, the same. You just have to pay attention here for the non-normal, and then you select this one. You enter the data. The variables we have here is the brightness, so you enter the data by clicking on the brightness, double click, so it will appear here. The distribution, since it says Weibull, then you select the Weibull. And the minimum percentage of population in the interval is 99 as given. This is how, or what I was trying to say in the previous example. This is not the confidence. It was 95 there by the chance, but here it's 99. So you have to write the 99, and then you press OK, and the plot will come to you here. The p-value, again, it says that it's 0.178, and that's mean it's Weibel fit. It's fitting the Weibel distribution. This is to double check the fitness of the data or goodness of fit test. And then the lower and upper are given here, 69.05, and the upper is 89.68. So these are 99. Now the manufacturer, 95% confident that at least 99% of all the batches of bulbs will fall in this interval. So the 95 is the confidence, and the 99, at least all of the batches, 99% of all the batches will fall between the 69.05 and 89.6. Okay, that's the difference, or let's say the achieved confidence. That is 59%. This is something that just from the results, but we have to pay attention how the entry for the required passing or the required products or service transactions to fall within the transactions, those considered to be the one are entered here, as we said previously here. This is different than okay, I think yeah, there is a mistake here. For the, okay, yes, here we go. Yes, here is the confidence level is 95%, and this is the confidence level in terms of implementing the analysis. نسبة الثقة للتحليل اللي انت عملته. But that percentage, and by the way, the tolerance interval, as we did previously, here now we selected the two-sided instead of the lower bound in the previous example, because the previous example was requiring the lower bound for the light bulb. Here, the light bulb lifespan, here he wants to have a lower and upper for the brightness. So he doesn't want that paper to be very shiny, يعني مرة كده بياضها يعني مشع لدرجة مزعج, and also he doesn't want it to be very low. فيبغى نسبة السطوع حق الورقة بنسبة معينة. So he selected the two sides, so he wants to find the tolerance between the upper and the lower. هذه نسبة الثقة لعملية الاناليسيس. But the percentage here نسبة وصول أو من منتجي أو خط الإنتاج حقي اليومي أو حسب المترك اللي أنت مستخدمها، كم من منتجي من ناحية النسبة حيكون within this tolerance level. فكم منهم حيكون within this tolerance level. This is what it tells you. 95% confidence that at least 99 of all batches يعني will fall in this interval. يعني 99% من الباتشز أو منتجك حيكون ضمن ال 69 and 89, between the 69 and 89. Hope that is clear, and don't forget the p-value. We use it to check for the distribution fit or goodness fit for the data. Okay, so let's move on to another tool, and also it's a new tool and very useful tool, type 1 gauge study. Type 1 gauge study, it's a new tool that maybe you have not used it before, but the concept behind it is it was discussed in the Six Sigma review, also in the quality control. We always talk about the consistency and the accuracy. What does it mean? The precision and the accuracy. The precision and the accuracy, they are very close to each other, but they are different. And in the quality, we distinguish between them, and we be careful between them, because each one of them refer to something different. So the type 1 gauge study helps you to determine whether the measurement system can measure parts consistently and accurately. That's mean precise and accurate at the same time. What is the difference between precision and accuracy? I put this figure to make it clear for you. So imagine if this the middle point in the middle circle, where is the pointer, this is the target. So if you have a low accuracy and low precision, that means they are scattered away from the target. But if you have high accuracy but low precision, that means what? You are very close to the target, but you are not consistent. You are not precision. Your precision is low. That means every time you are away from the previous reading, even though you are very close to the target, but every time you are away from the previous readings. يعني في كل مرة يطلب منك أداء عملية نفسها، خلينا نقول التارجت لإنهاء العملية 5 دقائق، أنت بتكون مرة 4، مرة 4.2، مرة 4.4. We are talking about something that whereas الفراكشن هذه حق المينت make different, or hours. You can put it days, you can put it month. Instead of time, you can put it in engines, life years. فإحنا هنا مجرد for example. If we have high precision but low accuracy, you are away from the target, but every time you are getting the same value. يعني every readings or every trial is the same. يعني as someone has، خلينا نقول كده very example very easy كده بسيط، واحد التارجت حقه A+ يكون all the time. Okay, here عندنا in this case يعني واحد بياخذ C D، بالماكسيمم أخذ واحد B بلس، أو واحد A مثلا، والباقي كلها B C D F مثلا. This is low accuracy, low precision. His target, it's away from what is the actual. Here, he has the same A+ as a target. Most of his grades are A or B+. So he is very close. Now, this case, interesting, that means he is consistent and precise. Having, let's say, here B all the time, 80, 80, 80, or 82. All the grades are 82. What is his target? Is 95 and above. Okay. The best one, where is the accuracy and the precision are high. So every time he's having a high grades above the 95. So every time he has A+. So he is achieving his target. And when he repeat that over and over in the courses, he is achieving the same grade. So the accuracy and the precision is about achieving the target every time. Okay, no matter how many times you are going to conduct that process. An engineer, and this is the example, excuse me. An engineer wants to certify an ultrasonic measurement system that is used to measure the thickness of a protective coating on painted doors. The engineer obtains a reference sample with known coating thickness of 0.025 inch. فهذا الريفرنس حقه. So this is target, A+ in that example we were talking. an operator measures the reference panel 50 times. So this is the sample, 50 times. The question says, determine if the measurement system can measure parts consistently and accurately using the tolerance range 0.0007. فإذا عندي tolerance range, pay attention. The tolerance range means the difference between the upper and the lower specification. Okay, here it's given as a range. It could be given as a specification limits. Let's say 0.025 plus or minus 0.03. Then you have to subtract. You add 0.025 to 0.03, and then you subtract it from the minus. So you have to get the tolerance in that case if it was not given. And you have to pay attention, I mean, between the tolerance range or specification, or it maybe give you not the plus or minus, I mean, it gives you the upper specification itself and the lower specification. So in that case, you have to get the tolerance range by calculating that one. So we need the tolerance, so the acceptable, in this case, the tolerance range to be 0.0007. How we do that, the data here for the thickness measures for the 50 samples are given. I will give you time to pause also if you would like to. I know it's a long numbers, but in case if someone interested in copying the numbers here and try the tool at home. Okay, how we do it? Very easy tool and also useful at the same time. We go to gauge study, we select the first one, type 1 gauge study. We will not cover the other gauges. They are about the reproducibility and repeatability, similar concept, but with different constraints and where you use them and when you use them. The data here we have for the thickness are given in the column. So basically you will have this row as we did before, empty like that. So you double click here on the thickness and then it will appear here. The reference is 0.025. That's mean the reference measurement for the thickness we have 0.025, like the A plus in the example I was mentioned. And the upper lower specification is 0.007. You can apply this example to your grades. Let's say the target is 100, the reference is 100, okay? And the upper lower specification, it could be the 5 grade, so you don't be less than the 95, and you can use that time lower only or upper only, depend on the case you are targeting on. But this is very easy application to do. After that, you press OK. Now, when you press OK, this is how the gauge study. What we care about, there are 3 parameters or values. Those are what we are looking for, and pay attention to those values because those are the key measures here. The first one, the p-value for bias, and the p-value for bias is 0.02, and it is less than 0.05, and that engineer can say that there is a statistically significant bias in the measurement system. So البايس here عكس الحيود اللي هو when you are biased معناها أنت مع جهة معينة أو مع قراءات معينة all the time regardless about the correct of those measures. So if it is less than 0.05, then the engineer can say في significant bias in the pressure in the measurement system. For other gauge here, we have to look for the CG and the CGK capability. It's similar to the process capability, CP and CPK. The same, you have to find those values has to be greater than 1.33, as we have for the CP and the CPK, okay? But those calculated here only for the measuring system. So if they are less than 1.33, as we have here 0.5 for the CG and 0.42 for the CGK, then they are less, and we can say that the measurement system is not capable to, and it needs an improvement. The third value you have to look for all these three, and each one, as we now explaining, is a different identification you give or you conclude from that value, which is the repeatability, the variation in the repeatability and the variation of the repeatability and the bias. Those values has to be less than 15%. So 15% or less, this is acceptable. But if it's greater than the 15%, that means variation is large in the measurement system. So here it shows you the variability. That means it shows you the variation of the measurement. Here it shows you the capability of the measurement. Here it shows you the bias of the measurement. Here it has to be less than 0.05 to say, sorry, it has to be greater than 0.05 to say there is no biasing. So if it's less than 0.05, that means the biasing is very significant in the measure system. And for the capability, if it's less than 1.33 for the CG and the CGK, that means this process is not capable. Both they have to be less than 1.33. And the last one is the variability. It has to be less than or equal 15% to say that the variation or the variability is acceptable. You interpret each of those three different values independently in the question you have to examine the gauge study of the thickness. Now, relating this to the accuracy and the precision, the variability shows you that you have a lack in the accuracy. The biasing, the same, it shows you that you are away from the target. The capability, that means you are not able to maintain the target and repeat it every time with the exact value. Okay, so these how those values can be useful, and this tool is a very useful tool and easy to implement and gives you information about your status. Moving on to our next tool. Our next tool is create attribute agreement analysis worksheet. This is again one of the tools that can be commonly used and very easy tool, by the way. There are two tools. We will deal with them here to the same concept. The first one is you create the agreement analysis worksheet first, then you use it to do the agreement analysis. So first one, we create this worksheet for the agreement analysis. What is the attribute agreement analysis? First, let's define it. The agreement analysis worksheet is used to assess the agreement of subjective ratings or classification given by multiple appraisers. عدة محكمين. Okay, محكمين, let's say for your project report or for noise level for a product, for engine, or for a vibration level for a device, or any value can be attributed in terms of high, low, medium, يعني in a scale of attribute data, not a variable data. Okay. وحددت these values حتى لو كانت يعني those values are numbers like 95, 80, 70, okay, but they are attributed, scaled in terms of the reference. حددت محكمين to evaluate this standard evaluation for the samples I have. يعني عندي sample of your project report, and the project report assessment following a scale 1 to 5 or 0 to 5. Okay, 5 means high, 0 means يعني nothing, no grades at all. Okay, and 1 is low and so on, or maybe 1 to 5, depend on the case. بعدين أخذت 5 appraisers, let's say 5 appraisers يعني محكمين خارجيين, and I want to give them all the project reports, and they evaluated based on this reference I have from 0 to 5 or 1 to 5. Okay, those reports already graded, يعني already the grade for from 0 to 5 or 1 to 5 is already placed, but it's hidden, they don't see it. I would like to match their assessment compared to the standard. Now, the original measurements or the original grading was the standard, okay? And those appraisers and مقيمين, we would like to see them how they are close to the standard. We can give them the same sample more than one time randomly to see every time are they going to give the same assessment or no. This is the concept of the attribute agreement analysis. فهو جدول. أول شيء we are going to do the worksheet, ورقة العمل لعملية التقييم. المحكم أو المقيم هذا أوكي بقيم عمل already تم تقييمه بستاندرد معينة ثابتة. إحنا نبي نشوف المقيم هذا في كل مرة يقيم فيها العمل هل بيقيمه بنفس الستاندردز، بيعطينا نفس قيمة الستاندردز ولا بتكون مختلفة؟ هذا الهدف من this tool. Why we use it? To make sure that if there is يعني evaluators or people that are assessing work, they have to be consistent. Again, we come to the consistency and the accuracy. Okay, dual precision with accuracy. Okay, this is again, but here in different point of view, we want to see how they are assessing standard work. Before we do the analysis of analyzing their assessment, we would like to create the sheet. How we create this sheet so they can analyze our standard work. The example is given here. Educational testing company hired 5 appraiser. عندي 5 مقيمين يسموهم to evaluate the written portion of a standardized essay test. إيش هيسووا؟ هيقيموا جزء خاص ب جزء الكتابة written portion for standardized test like TOEFL، خلينا نقول اختبار التوفل أو اختبار اللغة الإنجليزية. فهو جزء محدد يعني الستاندردز حقه ومقيمة أيضا، لكن التقييم حقها يعني مخفي عنها. To complete the training, now they were in a training how to، طبعا ما تحطهم على طول تقول لهم قيموا from 1 to 5 كده. They were in a training to show them when we say this portion deserve 1, when this portion deserve 2 يعني الريبورت هذا deserve 1 ولا 2 ولا 3 ولا 4 ولا 5 انت تحدد تدربه. Each appraiser must be able to rate say consistently, again here the consistency, with standard attribute numeric ratings. Attribute numeric ratings here given in this manner, ما هو from 1 to 5, they have different scale, -2, -1, 0, 1, 2. It can be 1, 2, 3, 4, 5. يعني هذه attribute numeric ratings based on the example here. Each appraiser rates 15 essay one time for each essay. هنا in this case the appraiser المقيم evaluate 5 sorry عفوا evaluate 15 essay يعني 15 report بس كل واحدة مرة واحدة one time that have a known standard. شوفوا في there are known standards يعني already we know ahead what the value for each one of those essay. Create data collection worksheet. Now we are not analyzing, we are creating the sheet. يعني التمبلت اللي we are going to use it then for the analysis. Create the data collection worksheet to collect the ratings from the appraisers in random order for the given information. So we are going to create this sheet so we can collect later their assessment for those samples. The numeric standards are given as you can see it here. 2, -1, 0, -2, 0, and until you achieve the 1. And the appraisers names Ahmed, Khalid, Ibrahim, Umar, Ali, those are المقيمين or المحكمين. Number of replicates here, since it says one time only for the sample, so the number of replicants is 1. Basically, in the ideal case, you don't use 15 samples. You use more, you use at least, it is recommended to use 50, and the replicants has to be 2. So the minimum at least 2. يعني the appraiser عشان نقول في we can say accuracy and precision, we have to repeat it and see the accuracy and the precision how it works. Okay, the consistency, we need more than 1 replicant, but this example just to show you how you use the tool. But in most cases, or in the ideal cases, you use at least 2 replicants. That means the appraiser to evaluate more than 2, and the sample has to be 50 or above. Okay, how we do the create the sheet. This is now the creating the sheet. The second tool we will do how we analyze this sheet between those appraisers. So let's go here, we go to create. So there is difference between create, attribute, agreement analysis worksheet, or attribute agreement analysis. Here you do conduct the analysis. You say this appraiser has done this amount of accuracy and precision. Here you create the sheet to collect their input, and then you analyze it here in the second tool. So the create the sheet, this window will open. You select the third one here, sample standard attribute in numeric values, because we have numeric values -2, -1, 0, 1, 2. If you have unknown, you select unknown. If you have text, if you have in other worksheet, so you are going to export it. So here in most of the cases, the one that we are going to use is the numeric values. Number of samples, we have 15 essays, so you put here 15. And number of appraisers اللي هم المحكمين أو المقيمين أحمد خالد إبراهيم, so you put them 5 and you write their name here. You can type it here, okay? And then with the same order, by the way, if appraiser 1 Ahmed, then you put Ahmed, then Khalid, then Ibrahim, okay? because now we are going to enter this important column, the numeric standard. The numeric standard, you put it as it is given here. It's giving this standard 2, -1, 0, -2, so you put it in the same order for the 15 sample. Why? Because those are the standard. The sample 1, let's say, the standard was 2, so you don't put a value randomly here, -1 or 1. It has to be as it was the standard, the original standard. Sample 1 was deserving 2. So this order, it will be given to you. You have to put it in the same order, okay? And the number of replicants is 1, as it says that one time each appraiser will evaluate the data, okay? And then you press OK. Yes, there is no more information needed. Then you press OK, and that will appear only to you. And then a worksheet will be created. This is going to be the worksheet that you are going to work on. Now you see the run order, that's mean the sequence, the sample, which sample? Sample 4, that's mean assay number 4. Sample 13 is assay number 13. And the standard already, that's already done earlier. It's already done by the company or by the trainer himself, an instructor. For sample 4 was -2, for sample 13 was 2, and so on. Now the appraiser اللي هو المحكم والمقيم اللي انت اخترتهم 5, Ahmed, Khalid, Ibrahim, Umar, Ali, all of them, and his input. Now you want to see his input when he evaluates sample 4. Did he give -2, or did he give -1 or 1 or 0 or 2? You put his input here, and that all for this tool until here, until now. The second tool we are going to use it is after you create the sheet. Now you just only create the sheet. If the question asks you to create the sheet, here where you stop. You don't do more than this. You create the sheet, you print this sheet here. This information is the total run, because you have 15 assay and you have 5 appraisal. Each appraisal will have 1 replicates, 1 at a time, so you will have a total of 75 runs. These are a summary of the information here, and the order, each one will run this sheet or create this sheet will have different run order. So it cannot be these 2 columns or these columns are the same for each one who does that worksheet. The standards are the same. For example, if sample 4 here -2, it will be always -2. But the run order for you, if you have implemented this example, maybe it will start with sample 13 instead of 4, or sample 2 instead of 4. So this column and even this one, it will be varied between one and other. And the same, definitely, the values here, if this one, it was sample number 2, so you will not have standard equal 2, it will be -1 here, okay? So this is to create the sheet. So if the question asks you to create the sheet, you create it in this manner and you stop here. The second tool, which we analyze these data, how we do that, similar example to the previous one. The attribute agreement now analysis to analyze the or assess تقييم the agreement. تقيم المحكمين the agreement of those appraisers of subjective ratings or classification given by multiple appraisers. فأنت عندك subjective rating 1, to 5 or A to B or whatever is it. multiple appraisers عندي مقيمين وعملوا عملية تقييم. I want to assess أقيم عمل التقييم حقهم. ف I want to see their accuracy and their consistency for each appraiser. The same as we did before. Now here we have the same similar example. Fabric appraisers مقيمين للفابريك اللي هو النسيج at a textile printing company rate the print quality of cotton fabric on 1 to 5 point scale. So عندهم السكيل here different from 1 to 5. The quality here wants to assess the consistency and correctness of the appraiser's ratings. The engineer asks 4 appraisers to rate a print quality on 50 sample of fabric twice in random order. Help the quality engineer in assessing the consistency and correctness of ratings to the standards for the collected data. يبغاك تقيم عملهم من ناحية accuracy والconsistency. Are they every time evaluated right with the standard or no? And how they are close to the standard. This is another thing. The precision and the accuracy. Remember, which one has the best match rates when within the appraiser? مين أحسن واحد كان يعمل التقييم فيهم يعني close to the standard? How many times Muhammad is one of the appraisers? You will see this in the data. Judge correctly across the trials. What is the overall accuracy of all appraisers' ratings? Those are very common questions to analyze the attribute. How we do the attribute analysis? You go to Stat, Quality Tools, Attribute Agreement Analysis. When you go here, this is similar than the one we have previously. The appraisers, المحكمين, his response, هذا التقييم حقه. A sample trial, because here each one he is going to rate the sample twice, not one, twice. فعندنا the first trial for Muhammad and the second trial for sample 1. Sample 2, the first trial المرة الأولى, the second time. And the standard هنا the standards اللي هو التقييم الأساسي الرئيسي أو المرجعي عندنا, okay, in column 5. Then we have all the data. I can have it here. If you would like to pause. Okay, this all the data. These are the entry data. It's hard to analyze it like that, so this tool is very useful to analyze those appraisals and see how they did assess those samples based on the standards. How we do that? We go to Stat, Quality Tools, Tolerance and no, I'm sorry. attribute analysis. So you select the response, the attribute column, that's mean the response, and the sample. So you select the sample number, and you select the appraisal from the appraiser name. And then what else? Standard here, because we have already the attribute already standard in our case. So basically, you select the standard from column 5 to put it here. So he will compare their assessment in the response here with the standard here. So the standard, the reference اللي هو المرجعي, you put it in this row. And also check on this one, select categories of the attribute data are ordered. So you the Minitab will follow the same order that you have already done here in the data. So basically all the information, column the response, and column for the sample, and column for the appraisal, and the standard. Yes, I believe that's all we have here. And the order, yeah, here, that's mean it will follow the same order that we have entered for the data or for the given data. When you press OK, then it will show you that the results as it's here. It's a long report. We will see how we analyze this report. Basically, you start within appraisers table, this one, the first one, and looking to this percentage and those appraisers, that will give you the answer for the consistency of each appraiser. Now, each appraiser, among others, how good he did. So all appraisers have a good match rate. So the least one was 86, and the highest is 100. And each appraisers have or provides 2 or more ratings for each sample. The engineer can evaluate the consistency in general for those or for each appraisers here. So if I ask you which one has the best rates for overall consistency among the appraisers, you can say here that's Amjad. But if the question asks you to evaluate the accuracy and the consistency, not only the consistency, so in that case, you will go to each appraiser versus the standard. Now, that's among or within the appraisers, between the appraisers, every time he is giving the same results. So this is consistency. But how it is close to the target or to the standard, this is something else. That's accuracy. Now, among those appraisers, the best one in terms of the consistency, Amjad here, and the least is Ahmad, usually, as usual. These are just an example here. Muhammad 90 and Bassam 96. So those in terms of the consistency. In terms of the accuracy and consistency, so now close to the standard or meeting the standard, and the same time, every time they repeat the assessment, they give the same result. So the best, again, is Amjad, but now the percent is 94. And how much he inspected. He inspected definitely 50 samples, and the match was 47. Okay, so if I ask you how many times Muhammad judged correctly, you will say Muhammad here 45 out of 50 with a percent of 90%, because this is about the accuracy, the consistency, how when you repeat it you get the same result, but here how it is matching the standard. So here is the correct across the trials for Muhammad. For Amjad, 47 out of 50. Moving on to the last one, we are now having the accuracy. The accuracy, we have covered the consistency first, then consistency and accuracy, and now for the accuracy. For overall, in order to say the accuracy for the appraisers, you can judge it by this percent. You have 74% overall accuracy for the appraisers. 37 were matched out of 50. So to answer the last question, what is the overall accuracy for all appraisers ratings, you will say 70% with 37 matched correctly out of the 50 sample. For the second question, we just answer it here. How many times Muhammad has scored correctly or assessed correctly? You will say 45 out of the 50 or 90%. If the first question, which one has the best match rates among the appraisers in terms of the consistency, we say that Amjad, he has 100% 50 matched, but now here we're talking about matching with himself across the others and across the trials, okay? Not meaning that is meeting the standards. معناها بيقرأ 3 مرات بنفس 3 مرات بيجيبها بنفس النتيجة. Remember the B+ guy when we had that example here. See, he's repeating, getting the same results, but he's not meaning that he's in the standard, okay? Also, he's good in the standard, but Amjad not, let's say here, he's very close in terms of the standard, but maybe here next to the circle, because when we go here to the accuracy, Amjad has 94, that's mean around the target, but they are accurate, okay? So this is how you interpret the attribute agreement analysis and how you create attribute agreement analysis worksheet. I will stop the recorded session here in this tool, and we will continue in the next session with the acceptance sampling and acceptance samplings for attributes and variables. Those are explained very well in other videos. I will refer to those videos, and I will briefly give two example, one for each of those accepting sampling. Then we will continue with the multivariate chart, variability, symmetry plot in the next session. Thank you for watching this and hope it was useful. See you in the next session.